So guys, welcome to day three lecture, the perceptron model and activation functions. So what we have covered in day two lecture. So we have covered the history and types of neural networks in details. We have covered the early development of AI and neural networks. We have also covered the perceptron. What is perceptron? Perceptron is an artificial neuron unit inspired by our biological neurons. So we looked up first we covered the differences between artificial intelligence, machine learning, and deep learning, and then we have also studied the different types of neural networks. We have covered multi-layer perceptron. These things we have covered in brief. We will dig deeper into them in later lectures. What we have covered till now, we have covered multi-layer perceptron, artificial neural network, convolution neural network, recurrent neural network, GANs. We have looked autoencoders, and basically we have seen a perceptron unit which resembles our biological unit, and we have also looked on multi-layer perceptron where there are many hidden units. So basically we know how the working of a single neuron, a perceptron unit, works. We get a weighted sum plus adding a bias, we get z, which is the weighted sum, uh, the input into weights plus bias. So x1 and x2 are inputs, w1 and w2 are the weights, p is the bias. So basically we get a linear equation. Here we can look that we have created an ANN model, which ANN is because basically a tabular data is passed in ANNs. So we have looked that how we get the equation, we get the weighted sum after each calculation, like for weights going for the Z1 here in this single neuron unit, we get W1 1. You can see the in superscript we have written 1. So basically it's x1 going here, and then x2 going to this unit, and then x3 going to this. So basically we are getting z1. So x1 gone to this will be multiplied by w1 x1, and then basically x1 is going to here. So this will be w1 x1, and then x2 going here to x2 is gone to this again, a neuron unit, then w2 x2. So then the up superscript we have written the weight. So basically weights of basically that particular neuron unit. Basically, weights are attached to inputs, but for better representation, we have given a superscript to it. So we can see that W1 1, W2 1 here, which is written. It is basically x1 multiplied by w1, x2 multiplied by w2 1, x3 multiplied if we and basically if we write more weights here, x3 multiplied by w3 superscript 1, x4 multiplied by w4 superscript 1 plus bias will give us basically uh, the Z1, which is coming here, which is the weighted sum plus adding the bias of this particular neuron plus passing it through the activation function. We'll be studying activation function. So basically, it was hard to calculate in this, so we covered the calculation in a simpler model, more simpler model. To for better understanding, we have drawn this simple model, and then we calculated the equation. So x1 is passing through this. So basically, all the inputs are passed to all the neuron unit, and then we basically a perceptron unit, and then weighted sum is we find weighted sum, and then we calculate z, and then we pass it to activation function, and that the result of the activation, the y output, is basically passed to next layer of neurons. So basically, for z1 here is the z1 thing. If you see, this is the z1 thing. So x1 w1, if we write w1 x1 here, superscript 1, and then we also write x2 for this, and then we get a z. So basically this z1, if you see, is of this. Basically this z1 thing is of this particular neuron, and then z2 thing is of particularly this neuron. Z2 for this, z1 for this. and then we get the bias. Basically, this thing we have covered, and then we pass it to activation function to get the Y output, which will be passed through this particular output unit. We have also looked in convolution neural network thing, where we have seen the input layer. There are many layers in convolution neural networks. So we have seen input layer, convolutional layer, pooling layer, fully connected layer, and output layer. We will be studying about these different types of layers. What does the convolution layer does? What pooling layer does? What fully connected layer? Here, this is all the fully connected layer, where tabular data or tabular data is basically passed. In convolutional neural networks, grid type of data is passed. That's why we have image. Image is a grid type of data where we have assigned values to a pixel. So this will be covering in a little part of our lecture. So CNNs are basically used in image processing and medical imaging, OCR, object character recognition. So basically, this CNN helps in grid type of data. And then we have seen recurrent neural network, basic of recurrent neural network, and we also have looked in GANs how synthetic data is basically created using GANs, and then we didn't do live coding. So today in today's lecture we will be doing live coding also, and then we have seen convolution neural networks, their advantage and limitations. All these things are covered. We have seen autoencoders also, and then our introduction to artificial neurons we have seen, and then we have also seen this diagram where we got the knowledge that how our neuron thing mimics the biological neurons present in the cat brain, or in general in any human brain, also animal brain. So today, moving to today's lecture, day 3, the perceptron model and activation function. So we basically know what is a perceptron. A perceptron is a neuron unit. Which is, a perceptron is basically a neuron which mimics the biological neuron. So it mimics the behavior of a single biological neuron in the brain, where it takes multiple inputs, processes them, and produces a single output. So this perceptron thing is introduced by Frank Rosenblatt, and components of perceptron we have seen input layer. Yes, we have already seen in this diagram. We can also see, look here. So this is basically a perceptron, and we have input layer x1, x2, x3. Basically they have written 5 x1, x2, x3, x4. You can see my, if we, yeah, now if we draw x1, x2, x3, and x4. Yes. So this x1 will multiplied with w1, x2 multiplied by w2, x3 multiplied by w3, x4 multiplied by w4. So basically x1, x2, x3, x4 are the inputs, and w1, w2, w3 are the weights. So after multiplying plus adding a bias term, we get z, basically z. We get z thing, or we get an output of this weighted multiplication plus addition of the bias term, and then we pass it to step function or activation function. In case of perceptron, we have a step function, which means that if wx plus b is greater than equals to 0, then it will be 1, and if it is smaller than uh, if it is smaller than 0, then it is 0, and then we get the output, basically final output. So this thing we have already looked in last lecture. We should read this thing. The input layer, the perceptron receives a set of inputs typically represented as a vector. So this thing is typically represented as a vector. And then we have associated weights W1, W2, and W1, which is multiplied with respective inputs. And then we have a bias constant term, which is added. Bias is basically related to a neuron unit, and inputs are related to weights are basically related to inputs, and bias is basically related to bias is basically related to a neuron. So there will be a bias for a particular perceptron or a neuron, and for weights are related with inputs. So for every input, there is a particular weight, like for x1 it is w1, for x2 it is w2, for x3 it is w3, and it goes on. And for a neuron, particular neuron or perceptron unit, we have a bias term associated. Bias term is not associated with with inputs. Bias term is not associated with input, but bias term is associated with a particular neuron. So a constant value, it is a constant value, typically initialized as one or a small random value that adjusts the output to improve model accuracy. And then this thing is passed with an activation function. The perceptron module formula. The perceptron performs the following mathematical operation. This thing we have already covered, and we know what basically happens, that inputs are multiplied by weights, and then a bias term is added, and then we get this z thing, and z is weighted sum plus bias, and the result z is passed through an activation function to produce the final output. If it is a binary classification, what is binary classification? You must be knowing. A binary classification is if there are two classes and we have to divide our data points between two classes. So this is a binary classification represented by either zero or one. So basically, there are two classes, zero and one, and then we classify the data points in zero and one. So here we have an example of perceptron. So imagine a simple AND gate. So AND gate, you must be knowing that what is AND gate? AND gate is basically if we pass 1 and 0. So the output will be 0. If we pass 0 and 0 as input, then the output will again be 0. And if we pass 1 and 0 as input, then also the output will be 0. But if we pass 1 and 1 as input, then the output will be 1. So basically, this is how the working of AND gate. This is how AND gate works. So imagine a simple AND gate where the inputs can only be 0 or 1. So basically, we have input as 0 and 1. The perceptron must output 1 if both inputs are 1 and 0 otherwise. So the same thing which I just explained. The model would learn the weights and biases that the perceptron mimics the logic of an AND gate. So I have generated a piece of code, and the logic here is written in this thing. So we will run this Google Colab book to understand. So we imported a NumPy library, and then we have made a function name as perceptron. We are giving the input, and then we have also passing weights and adding a bias to them. We have also passing a bias term, and then we are calculating the weighted sum plus adding a bias. And this is the logic, basic logic. So return 1 if z is greater than 0. We looked here that if this thing is also equals to 0, step function where z is greater than 0, then return 1 or else 0. So this thing here, if we basically write this thing. So if here this logic is written as step function, where for this logic basically we have corrected the step function, this activation function, but for different logic it will work differently. For our AND gate purpose, the step function where z is greater than 0. Uh, if z is greater than 0, then return 1. So if step function where z is greater than 0, return 1 or else 0. So basically, the this is the logic behind AND gate, and AND gate inputs, we are passing the inputs. So 0 0 is one input, 0 1 is another, 1 0 is another, 1 1 is another input. So here 0 0. So we are passing inputs as x1 and x2. Once the value of x1 and x2 is 0 0, the next time we are passing it the value of x1 as 0 and x2 as 1, and then we basically doing this thing. So weights, we are assigning sample weights, and we are also assigning a bias term. These are the random weights and bias which we have assigned, and then we basically predicting the z thing, where uh, we are getting the output c. the output which we get is same as we understood how the AND gate works. So basically, uh, we have written the logic here, and we got the output. Now the next piece code snippet is basically we are running for 10 epochs, and we have a learning rate, and then we are getting train weights and train bias. So this, if we study this part thing, yeah, the perceptron learning tool. So basically, the perceptron uses a simple learning tool to adjust the weights during training. This is how it learns to map inputs to correct outputs. So here we basically we if the prediction is incorrect, the weights are updated in the direction that reduces the error. So the perceptron learning rule. So this thing is basically if you have studied already looked if you have studied gradient descent, then this thing is basically works on the same way. And so basically, we have W new is equal to W plus neta. Neta is the learning rate, Y true minus Y predicted into X. X is the input. So basically, here we have W is the current weight vector, W new is the updated weight vector, neta is the learning rate, and then y2 is the actual class label, y predicted is the predicted class label by the perceptron, and x is the input vector. So y2 is the actual, which is the ground truth actual label, which we already know, and y2 is the predicted class label, which is predicted by our perceptron or a neural network model. So weights are adjusted only when a misclassification occurs. So if y true is equal to y predicted, so misclassification doesn't occur. No, no. So basically, if y true is equal to y predicted, then everything is fine. Everything is going right. But if y true is not equals to y predicted, then that means that misclassification has occurred. So weights will be adjusted when misclassification occurs. The learning rate controls how aggressively weights change. You must have studied gradient descent. You must be knowing how the learning rate thing works. And the perceptron converges when all training samples are correctly classified. So basically, everything converges down when all the training samples. Here, the training samples. If you know, we have already uh, know that our training samples are 0, 0, 0, 1, and then we have 1, 0. For all the perceptron converges for when all training samples are correctly classified. So when 0, 0 is classified as 0, 0, 1 is classified as 0, and 1, 0 is also classified as 0, and 1, 1 is classified as 1. Then all our training samples are correctly classified. Then this means the perceptron converges. So basically, this thing works like this. So I have also a piece of code written here. This is our piece of code. We are basically making a function train perceptron, and then we are passing the x numpy array of inputs, and then we are passing the outputs as we have learned from here. And also we know the logic of AND gate, so we are passing the both input and output, and then running 10 epochs. Basically, we are doing iteration of 10 epochs for weights and bias to get updated, and we are using learning rate as zero point 0.1. So basically, we have randomly initialized the weight and bias term, and then we are running the loop. Here, the thing is, the most important thing which you have to notice is that weights here in the formula of weight, basically the input term is coming at, but in the case of bias, there is no input term coming. So this thing I already told you in previous lecture or in this lecture only, I have already told you this thing, that the weight when we make calculation or weight updation, then we include the input term, because for every you already know this, for every input term there is a weight associated. So the same thing implies here that for updation also the input weight must be put down in the equation. So this is basically the logic behind it. For that, for every input there is a weight associated, but for not every for basically the bias is attached, or basically we can say bias is for neurons. Uh, for different inputs, we can have same bias if it passes through the same neuron. So basically, then we get written W and B. We will get the weights and bias, and if we run this thing, we get. So this is a randomly assigned. If we run it again, I think the value will be changed. Yeah, the value changed, and if we run again, so basically, the weights and bias can be different if the answer, basically, if the output is coming correctly, the weights and bias can be different for the same input and same output. So if we run, we can see that every time the weights and inputs are changing. If we run it again, then also it will be changed. See. So if we try a hands-on calculation of it, if we take this basically zero point 0.5 as W1 and zero point 0.5 as W2 and minus zero point 0.6 as bias. So if we do a hands-on calculation, so if we consider, so if we write, uh, one second, because yeah, Z1. If we calculate Z1, we know the formula W1 x1 plus W2 x2 plus bias. So we are taking W1 as zero point 0.5, rounding off to zero point 0.5 and rounding off to W2 also. And bias term we are taking zero point 0.6 minus zero point 0.6. So if we take bias as zero point 0.6 minus zero point 0.6, so we know the input x vector. If we say we know the input vector 0, 0, and then we know that it's 0, 1, and then we know 1, 0 basically, and 1. We also know the attached output of it for 0, 0 input for 0 equals to x1, for 0 equals to x2, then the output is 0. And here also 0, 0, and 1. So similarly, if we do hands-on calculation, 0 0.5 into 0 plus 0 0.5, 0 minus 0 0.6, 0 0.6. So if we pass, so we are taking our step function, like if the value coming from the weighted sum is equals to 0 or is lesser than 0, then the value is 0. But if it is greater than 0, then the value is 1. So basically, if this value 0 0.6 is smaller than 0, so this value fz1 will give us 0. So this is correctly classified. Now, if we do calculation for Z2, similar calculation if we do for Z2, and so Z2Z, this will be multiplied 0 0.5 multiplied by 1 and 0.6. So again, just value 0 0.1. If we pass to our step function, then Z2, the value is 0. So this is also correctly classified. This is also correctly. Similarly, Z3 calculation will be same as Z2. So this is also equals to minus 0 0.5, and if we pass to a step function, this will also be 0. Now for Z4 calculation, 0 0.5 into 1 plus 0 0.5 into 1, basically W1 x1 plus W2 x2 minus bias 0 0.6. So this is bias term is equal to minus 0 0.6, and if we calculate 1 minus 0 0.6, it's equal to 0 0.4. So if we pass this to our step function, as we know, the function returns 1 when the value, the z value, the weighted sum is equals to basically, which is if it is the weighted sum is greater than 0, then the step function returns the value 1, and if it is equals to or smaller than 0, then it returns the value as 0. So here we get the 1 value. So this proves that for this weight, so basically as fz4, we the value which we get here is the predictive value is 1. So we can see basically see that for the predicted value and the ground truth, the ground value is same. So for this weight and bias, our model is running perfectly. Basically, our model is doing the correct classification. So there will be no weight updation because we know this is basically all the weights are updated and this value has come. So we have also seen our hands-on calculation on this thing. Now we will move to basically now we have seen till now we have covered the how the perceptron learning rule we have covered. Now we will look at the limitations of perceptron. The perceptron can solve only linearly separable problems. So we in nature we get mostly we get non-linear problems. Basically, you must be knowing that in data science course you have already read many basically many models, or we can say many algorithms which separate the data non-linearly. You must have started with linear regression, and then we you have gone through many algorithms like KNNs, which basically we do separations in non-linear data. We make the lines or hyperplanes, or basically we do things to separate the non-linear data because in nature there is basically non-linear data. It is hard to get a linear data, and there is basically linear data is not present in the nature. So the perceptron can only solve linear problems where the data points can be separated by a straight line hyperplane. So if it's a 2D problem, then we can separate by straight line. If a 3D problem, then we can separate by plane. And if the dimension increases, then we need a hyperplane. It fails on more complex problems like XOR exclusively or which are non-linearly separable. To solve XOR, we need multiple layers of neurons. That is where the multi-layer perceptron comes. So basically, multi-layer perceptron, we need, if we add many layers to a single layer perceptron, then multi-layer perceptron, uh, we get multi-layer perceptron. So for solving the non-linearity, we need a multi-layer perceptron with activation functions like ReLU or sigma. So to basically the solve the problem of non-linearity, we have MLPs, basically multi-layer perceptrons, and then we have activation functions like ReLU or sigmoid. So these things basically MLPs can learn non-linear decision boundaries and solve XOR successfully. Now we look at steps of perceptron learning algorithm. So the first step as we have seen in this thing, that we initialize the weights and biases. So here we can see it's written like initialize weights and biases with small random values. And for each training example, compute the weighted sum of inputs. This we have already done. Apply the activation function. These are the basically the steps which we have already seen. And then we have to calculate the error, the difference between true value, the ground truth, and the predicted output. And if there is a misclassification, then we need to update the weights using the perceptron learning rule. The perceptron learning rule we have already seen here. And for bias also we have seen in this thing. This is the biases learning rule. So repeat until the model converges. Misclassification error is minimized. In this example, our misclassification error turned out to be zero because all the classifications were all the basically all the inputs were correctly classified. So repeat until the model converges. That is misclassification error is minimized. Basically, in large model, we have to minimize the misclassification. So our next topic is about SLP versus MLP. What is single layer perceptron? SLP is basically single layer perceptron. A single layer perceptron consists of only one layers of neuron where inputs are directly connected to the output without any hidden layers. It is simple feed forward neural network used primarily for binary classification tasks. So basically, there are no hidden layers and the input are directly connected to the output. So structure of SLP, it has an input layer and an output layer, no hidden layers basically. Each input neuron is connected to the output neuron with a weight. So this is the output is compared as this we have already seen. This is the Z thing, Z equation plus we weighted sum plus bias, and then we pass it to activation function, and then this whole thing comes where X, I are basically this thing are the inputs X1, X2, W1 are weights, VB is a bias. Basically, it's written like so. This you can understand. This we have already covered. Working of SLP takes input forward. So X1, X2, this thing, whole thing till Xn is the input. Then we have applied weights and sums them. We are finding the weighted sum. The whole thing is same, which we have studied earlier. But the thing here is there are no hidden layers, and the input layer are directly attached to output layer, and the attachment, the strings which they are attached are basically there are weights assigned to them for so the same thing which we have studied, that there are weights assigned to each input. So basically we find this thing and we just pass directly to the pass directly to the activation function to get the output. So if we try to get, yeah, here you can see basically, this is the input layers. Input layers are directly attached to an output layer, and then we have this multi-layer perceptron. The left diagram is of single-layer perceptron, and the right diagram is of multi-layer perceptron. So there, in you can see in multi-layer perceptron there are hidden layer, but in single-layer perceptron the inputs are directly attached to the output node. So if this input node is attached to output node, there must be a weight if the and for this input node also there must be a weight, and for this input node there must be a weight, and for this also. And when we multiply x1 with w1, the weight associated with x1, and then we multiplied x2 with w2, x3 with w3, and x4 with w4, so we'll find weighted sum. And then bias is attached with a node neuron, so node or neuron, and then the whole thing is added and passed to an activation function. So basically, the key difference between SLP and MLP is that in SLP there is no hidden layer, but in MLP we have many hidden layer, even one hidden layer, and then there can be many hidden layers. So this was the key difference. Limitations of SLP works well for linearly separable problems. We have understood what is linearly separable problem and non-linearly separable problem, and does not use backpropagation, so it has limited learning capability. What is multi-layer perceptron? A multi-layer perceptron is an advanced version of perceptron that consists of multi-layers of neurons. So you can see that there are here in this example we have just a one hidden layer. But if we look, yeah, if you can see here are two hidden layers basically. So there can be a multi layers of neurons and parallel neurons, and then there are many layers of many hidden layers. So input layer receives input features, one or more hidden layers processes inputs non-linearly, and output layers produces the final prediction. So this thing also you can understand by looking at this thing. There are many layers. So uh, multi-layer perceptron can be translated to deep neural network. Basically, deep neural network are so we can call it a multi-layer perceptron. Only there are many hidden layers uh, uh, between the input and output layer. So this diagram suits very well. Yes, you can see the input layer, then one hidden layer one, then hidden layer two, then hidden layer three, and then the output layer. So this is the diagram of a multi-layer perceptron. Structure of multi-layer perceptron. Unlike SLP and MLP has at least one hidden layer between the input and output. Okay. Neurons in each layers are connected to all neurons in the next layer, fully connected network. So you can see neurons of each layer. If we say this is the neuron, it is connected with every neurons of the next hidden layers. And also if you look at this also, this is connected with this neuron is connected with all the neuron of next layer, and this neuron is connected with all the neurons of output layer. And for similarly this input node is connected to all the neurons or nodes of the next hidden layer. So the same thing is written here. Uses non-linear activation functions like ReLU, Sigmod, or TANH to learn complex patterns. Working of MLP. So the same thing we have earlier also seen. takes input features, passes them into hidden layers where each neuron applies a weighted sum and an activation function. Use non-linearity in hidden layers to learn complex relationship. Basically, the weighted sum plus bias which we get is passed to an activation function, which is ReLU or sigmoid in this case, because these they are useful in non-linear case. So we get an output. An output is again passed to all the neurons of another hidden layer. Compute the final output based on the output layer activation function. Okay, so output layers also have an activation function, and then the output is basically comes after the inputs are the basically the weighted sum of the output layer is passed to an weighted sum plus bias of output layer is passed to the activation function, and then we get the final output. Uses backpropagation with gradient descent to update weights and minimize error. Advantages of MLP: can solve both linearly and non-linearly separable problems, uses backpropagation, allowing it to learn from errors, and can approximate complex functions and relationship in data. So now the biggest topic for of today's lecture, and we can say it is one of the most important topics in deep learning playlist. What is an activation function? So what is an activation function? An activation function is used to introduce non-linearity in the output of a neuron, allowing the neural network to solve complex tasks that cannot be solved with linear models. So basically, we know that we always get most in nature non-linear datas are only present there is very hard they are very hard to find linear data. So what an activation function does, an activation function introduces non-linearity in the output of a neuron, which helps in classifying the non-linear data. So basically, an activation function, if we reiterate the definition, is helping to introduce non-linearity in the output of a neuron, which basically helps to classify the non-linear data. So this is the basic work of an activation function. So we will be looking into different activation functions, and it determines whether a neuron would be activated or not based on weighted sum of inputs. Why are activation functions important? Without activation functions, a neural network would behave as a linear model, reducing its capacity to learn complex patterns in data. So we need activation function because we always have a non-linear data. So this is the key benefit of or the key importance of an activation functions, because it helps to classify non-linear data by introducing non-linearity in the output of a neuron. Different activation functions are chosen based on the nature of the task. For example, classification and regression tasks. So common activation functions. We have sigmoid activation functions, then we have ReLU, rectified linear unit, and then tanh hyperbolic tangent function. So there are many this activation functions. And then the last part also we have of this lecture is we will be looking at different libraries, and then the role of mathematical functions in neural networks. So we go through the sigmoid activation function. So this is the sigmoid activation function. This is the formula of sigmoid activation function description. So the sigmoid function squashes input values into range between 0 and 1, making it ideal for binary classification tasks, outputting probabilities. So basically, sigmoid is used for ideal for binary classification, and this is the formula. The range of sigmoid function is the range is basically from between 0 and 1, and I have prepared a code here for a sigmoid function. Basically, this is the we have created a function sigmoid x. X is the input which we are passing, and then written this is the formula of sigmoid function. You can also see from here it is 1 upon 1 plus e to the power minus x, and this is basically the function or logic behind it. And xp numpy we are making, and linear lin space, basically we are from minus to 10 we are choosing basically in equal intervals we are choosing 100 numbers basically which are between minus to 10 in equal intervals, and then we are printing them and then passing to sigmoid function and printing the y. So if we look basically here, if we look this is the output y. This whole thing is the output of, and we if we look into it, we can find that the range is between 0 to 1. So if we also draw the graph for better understanding, so you can look that the range is from, it is asymptotic. So basically, it is not the line of sigmoid function is not crossing the axis, the basically the axis passing from the number one, which is parallel to x-axis. So it is asymptotic at 0 and 1. So its range is from 0 and 1. So we have drawn a graph of this for a better understanding. We did this. So you can look that it gives the probability. So if we multiply the any of this with 100, we will get the probability of a binary classification work, like finding basically, if a binary classification of dog and cat classification, we will get the probability like 80%, 0.8 for dog. So that will translate into 80% this image contains dog. And if we have an image of cat and the classification is basically the finding a dog in that, and then it may translate to uh, 0.2 the value 0.2 of possibility of finding a dog in a cat picture is 0.2, so that will translate to only 20%. So this is sigmoid functions helps in binary classification, and its range is from 0 to 1. The same thing is written here, the range is from 0 to 1. Use cases used in binary classification problems, logistic example, logistic regression, binary classifiers in neural networks. Disadvantages: vanishing gradient problem. For large positive negative inputs, the gradient becomes very small, leading to slow learning. So basically, you must be knowing vanishing gradient because many gradients are multiplied and then it squashes to very small. So this doesn't help the model to learn better because the learning becomes very slow. Not efficient for deep learning, the sigmoid function is asymptotic, meaning it approaches two horizontal asymptotes but never actually reaches them. So here you may think that it is reaching the one, but it is just appearing to be reaching one, but it never actually reaches. And so the same thing is written here. And then this we have another piece of code. You can run this code also. So you will get the output. You can see that the range is from 0 to 1, basically. If we are passing -2, -1, 0, 1, and 2. Now we go to rectified linear unit, ReLU function. So description: ReLU is one of the most widely used activation function in deep learning due to its simplicity and effectiveness. Mathematical formula, basically max of 0 and x is basically the input. So if we look the code, so again we are defining a function x, and then we are using the utility of numpy by finding the maximum of 0 and x. So again we are using linspace, and then we are getting a number between minus and 10 on 100 numbers between minus and 10 on equal intervals, and then we are printing it. So basically we get this thing as our input, and then we are passing it to y ReLU of x, and then we get the output. So if all the negative till 0 minus 0.1010101, we are getting 0, and then we are getting the number itself. So it basically maximum of 0 and 0x. So if a number is negative, that will be x will be a negative term, and maximum of 0, and that number will be 0. So we got 0, and then this is the simple thing you can understand. And if we if we try to plot it, we get this thing. Here the line is parallel to x-axis, and the value is 0. So this you can see here. And we made graph from -10 to 10 in basically uh, the the thing we defined, like from -10 to 10. So domain of x is from -10 to 10. So a range is from 0 to infinity, because you can look if a number is past 0 infinity, that the maximum of 0 and 0 infinity, and plus positive infinity will be positive infinity. Use cases commonly used in hidden layers of deep neural network. Advantages: it mitigates some vanishing gradient problem, making learning faster.
computationally efficient. Disadvantage can suffer from the dead neuron problem, where neurons stop learning if they are pushed too far into negative. So basically, if you can see that if a neuron, if there are many negative value passing through every time it is passing through that particular neuron, then it will always get a value equals to zero. So basically, it the more the basically that neuron can suffer with dead neuron problem. So this we have another piece of code, the same -2 in -1012 input is passed, and then the output is this. Going to another activation function, tanh. Tanh function is similar to sigmoid but squashes the output between -1 and 1, making it symmetric around the origin. So basically, in sigmoid, the range was from 0 to 1, but in tanh it's from -1 to 1. And the mathematical formulation is this: e to the power minus x minus e to the power minus x upon e to the power x plus e to the power minus x. So the range is from -1 to 1 if we look at the code. So again, we are using the NumPy utility directly, and this is the logic behind it. And we didn't have to write the formula because this is the NumPy is already having a tanh uh, in it. So the logic is already in that NumPy library. So we are using that thing, and then again we have already looked at this thing, and then we got the value. So till the this is our input, and then this is our out. So you can look like we there is a symmetry between there's a symmetry uh, from a y-axis if we say. It is also written that there is a symmetric around origin. Sorry, it's a symmetric around origin. Yeah, it's basically symmetric around origin, and you can see the values from -1 to 1. The range is from -1 to 1. And again, it is asymptotic. It is not basically touching or crossing that -1 and 1. Just it's getting closer to and closer to it. So advantage is tanh is preferred over sigmoid in hidden layers because it produces strong gradients for optimization, and disadvantages also suffer from the vanishing gradient problem. So this is the example basically. You can try this also example. You can see that the range is between -1 to 1, and it is symmetric from origin. Deep learning framework provide tools to build and train neural networks efficiently. Here are some of the most widely used libraries. So basically, this the next part is about different libraries. So the major understanding we are using here we are only studying three activation functions. So these are the three activation functions, and activation functions are very important because it helps in classifying the non-linear because they are introduce non-linearity in data set. Well, because they introduces non-linearity in neuron, which helps in dividing the non-linear data set or classifying the non-linear data set. They can be helpful in regression also. Basically, they help in regression also, not just in classification. Classification, it's easy to understand. So I was teaching more about classification, like the boundaries you can imagine. But activation functions also help in for regression thing because there is also a nonlinear data, and we looked on sigmoid activation function. The range is 0 to 1. Then ReLU activation function, and then we have also looked at tanh activation. We will be using these activation functions, and we will be seeing their use cases in different problems. On common activation functions. Now we will be looking on different frameworks used in deep learning. So there are different frameworks used in deep learning like TensorFlow, PyTorch, Keras, and there are some more. Basically, these three are major deep learning frameworks. So what does deep learning frameworks do? Deep learning frameworks provides libraries which have already implemented the different deep learning codes which we can use, which we can basically import to our models and then use them to run our models. So basically, deep learning frameworks provide tools to build and train neural networks efficiently. So we can import different libraries in these deep learning frameworks. These libraries have already been implemented
They provide tools to efficiently handle tensor operations, automatic differentiations, and GPU accelerations because basically they are providing us a framework which we use for different types of deep learning operations and usage. So we have TensorFlow, which is developed by Google Brain. We have PyTorch, Facebook AI researchers developed it. And then we have Keras developed by Francois Charlotte, later integrated into TensorFlow. This I will explain you. We are going into what are different deep learning frameworks. So this is the basic description. We will be looking at codes and how differently we use codes to achieve the same output. So TensorFlow developed by Google Brains. So the feature of TensorFlow is it is open source machine learning library, efficiently supports GPU and TPU acceleration. So GPU is graphical processing unit and TPU is tensor processing unit. Provides Keras as high level API for building models easily, used for deep learning, computer vision, NLP, and reinforcement learning purposes. So this is the basic description of what is TensorFlow. So we have a code. We will be running this code in our another few lectures where we will be differentiating by PyTorch, why we prefer PyTorch over TensorFlow, and we will be looking how the same code, the same output can be achieved by using TensorFlow and PyTorch or Keras. So this is just a basic description of the deep learning frameworks. Now we have PyTorch, which is developed by Facebook AI researchers. Features popular for research due to its dynamic computational graph, easy to debug and modify models during runtime, strong community support, and extensive libraries like Torch Vision and Torch Audio. Supports both GPU and CPU computation. And then we have example code of this also. Then we also have Keras. Keras is actually provides a high level API. If you see, it is written later integrated into TensorFlow. TensorFlow earlier versions were very low level, so you have to write complex codes. So Keras was used on top of TensorFlow, which provides a high level API for easy use of TensorFlow. So now Keras has been basically integrated into TensorFlow. So it is a user friendly and easy to build models. Works on top of TensorFlow, Theano or CNTK. So Theano or CNTK are also deep learning framework, but I think these deep learning frameworks are no more exist now. It is ideal for beginners due to its simple syntax. So basically, it provides high levels APIs which are very easy for us to because it provides easy to build models, and it is user friendly. TensorFlow was complicated in writing deep. Yeah, so the same thing which I told you. TensorFlow, the earlier versions were complicated, and writing deep learning models with it required a lot of code. Keras was created to make things simpler by providing an easy to use interface for building and training neural networks. At first, Keras was a separate library that could work with multiple backends like TensorFlow, Theano, and CNTK, but later TensorFlow integrated Keras as its built-in high-level API. So, which should we choose? Which one should we choose? Which basically framework which we should choose? So, we will be using both framework in our deep learning throughout our deep learning course, but PyTorch is likely better option because most of the research work is done on PyTorch, and most of the research paper, the implementation of codes are done on PyTorch. And PyTorch is basically here it is written more widely used in academia, the same thing which I told, and PyTorch is easier to experiment with, and the same thing is written useful for research purposes, works well with Hugging Face and vision models like spin transformer and diffusion models. That's why most researchers, including me actually, I also prefer using PyTorch. Mostly I use PyTorch for my research projects on medical imaging. So we will basically prefer PyTorch, but we'll be running code using PyTorch and TensorFlow both. Now we are at the end of today's lecture. We will be looking at what we have done today. First, we'll be revising what we have done. So we have covered what is perceptron. We have looked the step function, how the summation and bias, how basically the weighted sum is calculated, how then activation function and output is gained. And then we have run few codes to look how we will get weights, how first we assign random weights and bias, and then how the weights and biases are trained. We have looked SLP single layer perceptron versus multi-layer perceptron. We have also looked upon different common activation functions like sigmoid activation function, ReLU activation function, TANH activation function. Then we have also looked basically their graphs, and by graph we can infer about the range between which they work. And we have also looked on the deep learning frameworks like TensorFlow, PyTorch, and Keras. And we now we look at role of mathematical functions in neural networks. So purpose of activation function, we already know the purpose, because we want to introduce non-linearity. Basically the activation function introduce non-linearity in the neurons, and then therefore the it basically gives non-linearity to the whole model. So this is the purpose of activation function. And then we also have looked at how activation function control output range, because we know sigmoid produces output range in between 0 to 0 and 1. So this thing, and tan between -1 and 1. So this we already know. Choosing the right activation function, we know that sigmoid is great for binary classification. This we will be basically we will be seeing which function, which activation functions suits which type of model. We will be also looking at softmax function and ReLU function, when leaky ReLU function, when we will be running the code. So sigmoid is great for binary classification, ReLU best suited for hidden layers in deep networks due to computational efficiency, and TANH often used in recurrent networks or hidden layers, especially when data is symmetric around zero. So this we will be looking through code only. And applications in machine learning, binary classification. So these are the applications in machine learning: binary classification, sigmoid activation, which all we already know is used for binary classification and binary classification. Multi-class classification, we use softmax activation function. This will be looking when we will be doing the a multi-class classification problem. And deep learning, ReLU activation function in hidden layers for efficient training and convergence. Activation functions in proper libraries. So this is basically the code of how to import the activation functions in our code. So this also we will be looking in code only to understand. For better understanding, we will be directly understanding from code. So this marks the end of our day 3 lecture, the perceptron model and activation functions.